Okay, let's get started. Welcome everyone to today's University of Texas Energy Symposium for February 17th, 2026. I'm Kerry King, research scientist and assistant director here at the Energy Institute at the University of Texas at Austin. Let's get started. Welcome everyone to today. Before I introduce today's speaker, I will introduce who is coming up in the next couple of talks. Next week, we'll have Aditya Ramji. We'll talk about electric vehicle electrification, shaping industrial policy with vehicle electrification, analyzing global electric vehicle supply chains and implications. Following that, in 2 weeks, we will have a talk from Kelly Sims Gallagher. She's the dean of the Fletcher School at Tufts University, and she will talk about shifting priorities in U.S. energy innovation policy. Today, it is a pleasure to have Michael Craig. He is Associate Professor at the School for Environment and Sustainability, as well as the Department of Industrial and Operations Engineering at the University of Michigan. The title for his talk today is Decarbonizing the Electric Power Sector in a Warming World. Dr. Craig's Asset Lab researches how to decarbonize energy systems while making those systems robust to climate change. He's received funding from several federal agencies, including an NSF Career Award. He serves on advisory committees of several climate adaptation initiatives led by industry and national labs. He's published in the journals Nature Energy, Nature Climate Change, Joule, and other leading journals. And prior to this position at the University of Michigan, he worked as a research engineer at the National Renewable Energy Lab, now National Lab of the Rockies. He received his PhD in engineering and public policy from Carnegie Mellon in 2017. We'll summarize the abstract for today. Decarbonizing electric power systems in the U.S. and abroad will require deployment of low-carbon technologies from households to transmission-scale power systems. At the same time, intensifying climate change will increasingly threaten reliable access to electricity. So this talk explores Michael's work on interactions between decarbonization and climate change. He will specifically focus on effects on electric vehicle battery degradation, distribution networks costs, and the idea of dynamic line ratings for transmission. So with that said, please submit your questions as normal. I will hand over to Michael now and stop sharing. So please submit your questions as normal via the question and answer feature of Zoom, and I will try to interject applicable questions as if they seem applicable during his talk. Otherwise, I will hold them until the end. And with that said, welcome Michael Craig. Go ahead, Mike.
Great. Thanks, Kerry. Can you hear me okay?
Yes, I do.
Excellent. All right. Well, thanks so much. It's a great honor to present here. Everybody who works in energy knows UT Austin and the work that you all do. So I'm really glad to be here. And thank you very much for the introduction. As Kerry said, my talk is about decarbonizing the electric power sector in a warming world. Now, I will say right off the bat, maybe you read the abstract before coming here, and you noticed that I was also going to talk about households and heat pumps and insulation and rooftop solar. So I bit off more than I could chew, I realized, and so those parts have been put into the Q&A session. So if you want to learn about rooftop solar and how it can degrade under high heat, under climate change, or if you want to learn about interactions between climate change and households, I have all those slides. I'm just not going to present them here, so I can present everything else with time to spare. All right. So my job today is to convince you all, if you need convincing, that we need to plan for not just decarbonization, but also climate change if we want to achieve reliable, accessible, cost-effective, and low-carbon energy systems. And every utility across the United States would say their priorities are reliable, accessible, and cost-effective electric power systems. Those are the bedrocks of how we plan and operate power systems today. Depending on who you talk to, low carbon might also be a priority or not. But I want to convince you today that climate change and decarbonization have to be considered together if we're going to maintain these aspects. So just to give a very, very brief introduction to climate change, we can think of it as affecting two things: your average weather that you experience and your extreme weather that you experience. This is all the way back from 2001, an IPCC figure that just shows you the change in distribution of temperatures caused by climate change. you get this shift rightward, which again just means your average is warmer, you get a lot more hot weather, and then you're going to get records that you haven't seen before in terms of extreme heat. So climate change is going to drive both of those factors. And then decarbonization, at the most simplest, the most simplest way to think about it is to think it is going to drive development of new technologies, and it is also going to radically change the composition of your systems. Lots of other things have to happen to effectively decarbonize, but we'll just take a technology-centric approach here. So how are these things going to interact in general? Well, if we think of average weather, say it getting hotter on average, that's going to interact with your new technologies and the change in the system to drive changes in your long-run costs and emissions. So we want to capture that interaction when we think about these two factors. And then your weather extremes are going to affect your costs as well, but they're really going to affect your reliability and your accessibility. And there are lots of examples of this from the recent past. California 5 years ago, rolling outages during the summer during extreme heat that they had not experienced before. And so there you see extreme heat reducing your reliability of your system. And then wildfires are a great example of losing accessibility. You have public safety power shutoffs, you have direct damage to your infrastructure. So even if the power is there for you to get it, you can't access it. So we have to think about these things together if we're going to maintain reliable, accessible, cost-effective, and low-carbon energy systems. So again, what I want to do is demonstrate this to you and convince you of the merit of thinking about these together. And to do that, I'm going to present 3 different papers that are all on this topic of how decarbonization and climate change are going to interact. And we're going to work across scales here. We're going to start with electric vehicles, so a technology-driven assessment at the global level. Then we'll step up to distribution systems, electric power distribution systems, and finally, we'll end at transmission systems. So we're going to go all the way from the household scale up to the transmission scale and see these interactions happening at different scales. Like I said, households and rooftop solar would be in this upper bucket here. I'm happy to talk about those in the Q&A. All right, so let's start with electric vehicles. We'll get right into it. This is a paper that was led by Hao Chu, who is now a postdoctoral fellow at Stanford University. All right, so many of you might own electric vehicles. Maybe you've ridden in one. This is my first electric vehicle. This is a Chevy Volt that I bought while I worked at NREL. It was from 2017. I love that car so much. What a fantastic car. I owned it from 2017 until last year, so I had it for 8 years. And one thing about that car that I didn't love was that over time, you could tell that battery had a lot less juice in it. My maximum range went from like 50 miles on a good day down to probably 30, 35 miles. And so this is an example of an EV battery degrading over time. It's got the longevity is decreasing, the range is decreasing over time. And this is a really critical issue to consumers because you don't want your EV battery to degrade over time. And because it's important to consumers, it's also important to manufacturers. Now, a big driver of longevity of EV batteries is exposure to extremes, extreme heat and extreme cold. This is true from just empirical data. If you look across EV fleets and battery state of health across the United States, you can see about a 2-fold difference in lifetimes across climates just within the United States today. And on a global level, that difference is even stronger. So extreme heat, extreme cold, very important to determining battery longevity. And this figure on the left-hand side is from a paper from 2017. It's just driving home that point. You can see different temperatures at which the battery is operating. And the important thing here is that as you go from the blue down to the red, you're getting into higher and higher temperature regimes, and your state of health, which is a proxy for longevity, is declining over time. So your battery is suffering in those higher temperature extremes. So climate change, a hallmark of it is that you are going to get more extreme heat. And so we might be worried that climate change, by increasing extreme heat, could be reducing our EV battery lifetimes. So this essential decarbonization technology is going to be undermined by the very thing it is supposed to address. But one thing that we do know from recent years is that because battery technology has been advancing so much over the last 10 years, durability has really improved. This plot here on the x-axis, we have a lifetime coefficient. You can think of that as The higher the coefficient, the more durable the battery is, the less likely it is to degrade. And going top to bottom, you have you go from 2014 through 2020. These are years in which the batteries were released. So you can see a big rightward shift in that lifetime coefficient, batteries becoming more and more durable just over this 6-year time span. So if we look at this, we might wonder what would happen to EV battery lifetimes under climate change. When we look for those, we cannot find any papers on it. And so that's what we wanted to research. We wanted to first ask, how will climate change affect EV battery lifetimes? And EV battery lifetimes, we could also think of accelerate degradation. So the faster you degrade, the lower your lifetime is. And then we also want to think about how battery technology improvements could moderate the degradation that you're going to experience in the future. Given that we've seen such great progress in durability, will that help us keep batteries healthy as we move forward into increasing temperatures? All right, now I'm presenting 3 papers today. So the methods that I'm going to present for each paper are going to be abbreviated. I'm more than happy to get into details in the Q&A here now or at the end of the talk. But in general, what we want to do here is capture all the factors that will really matter when it comes to battery lifetimes into the future. Those factors are going to be, what is the climate or weather going to look like into the future? How do people drive and charge EVs? And then how do batteries respond to the driving, the charging, and the ambient weather conditions in which they exist? So we're going to start with our climate data. We're going to take 3-hour data and do some downscaling and bias correction to it just to make that climate data very high resolution, temporally and spatially. So we're going to get time series of weather going out into the future through mid-century. We're going to feed all that into a bottom-up simulation for EV driving. This is basically simulating EVs driving through cities and the cities that we're going to analyze across the globe. So we track where is it going, how fast is it going, when is it charging, where is it charging, at what rate is it charging. We capture all that in this simulation. And so that is partly a function of temperature. If it's hotter, you run your AC more. More AC means less range. We're going to take that driving behavior. We're going to include battery improvements, and we're then going to quantify battery degradation. This bottom here is saying the more you use your battery, the more you cycle your battery, the more it's exposed to extreme heat, the faster it will degrade, the lower the lifetime will be. And so ultimately what we get out from the degradation model is our lifetime analysis. We're going to quantify the lifetime of batteries if we're in a historic climate or a future climate, if we have old batteries or new batteries. And again, these lifetimes that we're quantifying, they capture climate change affecting weather, they capture your driving behavior, they capture the degradation of individual batteries. All right, so let's take a look at what some of the results are that we find. The first finding that we have is, let's think of old batteries. We're going to categorize old batteries as batteries that were released between 2010 and 2018. This is a map showing you the reduction in lifetime of those old batteries. And we can see the dark red here is a stronger reduction in lifetime on the order of 20%. The lighter red is less reduction, and the light blue actually is an increase in your lifetime. So in general, what you see here on the old batteries is a lot of dark red or light red points, indicating climate change is reducing the lifetime of those batteries. And I've dropped the color bar here. We will get the color bar back soon. We can take all these points. So we ran this for each of these cities across the globe, as you can see. We can take all these points and just put them into box plots at different levels of warming that we might experience. So on the x-axis here, we have ranges from 1 to 4 degrees Celsius of warming. 1 degree Celsius is pretty mild warming. 4 degrees Celsius is pretty extreme climate change. And so you can see these box plots, you get a change in battery lifetime on the order of 5% down to 15% if you look at those median values. But certainly there are parts of this distribution that are 20% or greater. So this is really showing you, because climate change is increasing extreme heat, you're getting large reductions in the lifetime of your batteries, of those old batteries released between 2010 to 2018. So this is concerning. 20% reduction in lifetime is a big deal. It means you're replacing those vehicles faster. It means the resale of those vehicles and batteries is a lot worse. So that could be bad for electric vehicles. But we mentioned that just in the recent history, we've seen great improvements in durability of batteries. So we want to compare old batteries versus a newer generation of batteries released between 2019 and 2023. And so we have the same right-hand box plot here is what we have on the left-hand side here. And now we've just put that next to box plots for new batteries. And we can see that while your old batteries had a steep drop in lifetime because of climate change, your new batteries do quite well. You get small reductions in their lifetime, but those reductions are very small. The median is much smaller, and even the lower ends of those distributions are much better than they were before. So we're seeing here that the improvements in technology that we've already seen in EV batteries is almost entirely wiping out the effect on lifetime that you would experience under climate change. So we have seen this top left map before. Again, that's where we have the different cities and their lifetime reductions. Here I've actually got the color bar included. And the bottom right now is showing the same type of map, but instead of for old batteries, it's for new batteries. So we can see a strong washing out basically. Places in India, for instance, where you had strong reductions in lifetime, you have a very slight reduction. In places across the United States, for instance, where you had lifetime reductions, now actually you get slight lifetime improvements in batteries because of climate change. That also occurs in Europe, for example, and in many parts of China as well. So this is showing you the same information as the box plot, just spatially. And again here, the takeaway is less red, red is turning to blue. We're going from lifetime reductions to minimal reductions or even slight improvements in your lifetime. We wanted to look at patterns in this heterogeneity across space. And so what we've done here is grouped countries based on their GDP, log GDP. So a higher GDP is a more wealthy country, a lower GDP is a less wealthy country. And on the top, we have our old batteries, these red lines. The bottom, we have our new batteries. And the different lines are for different warming levels. Again, 1 degrees is less warming, 4 degrees stronger warming. So we can see these downward trends in the lines, especially in the top figure. That's indicating the effect of climate change is stronger in your less well-off countries. If you're at a lower GDP country, you see stronger reductions in battery lifetime. If you're in a high GDP country, you see weaker reductions in battery lifetime because of climate change. So this would be particularly worrisome given that a lot of the electrification of fleets we would need to do are in these lower GDP countries. But with new batteries, again, we see it really mitigating a lot of this effect, especially at warming levels of say 1 and 2 degrees Celsius. You see very little effect or difference between income groups of countries. So reinforcing batteries are really improving your overall outcomes and addressing this regional inequity that you might see in lifetime reductions. We also did an analysis just asking why is this happening? What is climate change actually doing? If you work on electric vehicles, you might have two hypotheses. One is the temperatures increasing under climate change could make your battery hotter, and that heat in the battery is degrading it. Or you might be cycling it more because the hotter it is, the more you run air conditioning, the more you're using your battery. So we try to decouple these two effects. This figure, the middle of each of these subplots is cell temperature. The left-hand side is cycling, and the right-hand side is the combined effect of the two. And the takeaway here is it is the temperature of the cell, not the cycling, that's really reducing your lifetime. And so it really is temperatures increasing under climate change, making your batteries hotter, driving that degradation, especially in your old batteries, which is the top row. The bottom row is your new batteries, and you don't see nearly as much reduction. The y-axis here is like an order of magnitude different, basically. All right, so we looked at EV batteries. We know that technology has improved a lot. We wanted to understand how climate change would affect its longevity. And we found while we could have been worried about it with old batteries because we get huge lifetime reductions, when we think about new batteries, actually the situation looks a lot better. You get very little lifetime reductions. And so here's an example already of decarbonization and climate change working, interacting very strongly. In particular, the key thing here is that the technology change you got just from decarbonization, you weren't improving batteries for adapting to climate change. You were improving batteries to further decarbonization, to make those batteries more economic, more attractive to consumers. That has the co-benefit of basically addressing all your adaptation needs in your electric vehicle batteries. And so we get this very strong co-benefit of decarbonization onto climate adaptation, an important factor to think about. All right, so that was the first step, technology level at electric vehicles. I promised Carrie I would stop to see if there were any questions that I should answer before I move on.
Yeah, I don't see anything related yet to this particular topic.
Okay, great. All right, so we've got electric vehicles we've done at the household level. Now I want to step up one level into distribution systems. Distribution systems are the poles, the lines in your backyard, bringing power from our large-scale transmission systems into your neighborhood, into your home. And here we want to look at two factors. We've got climate change increasing the loading of your assets, and then we also have decarbonization driving electrification, which is also going to affect your loading. So we're going to look at these factors in the context of distribution systems. This is work led by a postdoc in my group, Aviad. And I'm going to cheat a little bit here. What this paper is going to be about is only about loading from climate change. We're going to qualitatively talk about its implications for decarbonization later. All right, so let's think about how temperatures could affect distribution networks. We've got a distribution system here. We've got a household, a pole with a transformer, and some lines connecting your household back to a substation that's stepping down your voltages. All right, increasing temperatures under climate change could drive more cooling at the building level. That's going to increase demand from buildings for electricity. And for the power lines and transformers, hotter temperatures are going to decrease the thermal capacity of those lines and transformers just based on the physics through which these assets operate. We're going to see higher heat losses at higher temperatures, and we're also going to see lifetime decreases. So all of these factors are going to occur under climate change under increasing temperatures. We could do a rough order of magnitude estimate for how much this could matter. We could look at temperatures increasing by 10 degrees Fahrenheit, let's say just during an extreme heat wave. And 10 degrees Fahrenheit could seem unreasonable, but in the Pacific Northwest heat wave about 5 years ago, that is exactly what they had happen. That heat wave shattered records. It was like 10 degrees Fahrenheit warmer in some regions than it had ever been before. So 10 degrees Fahrenheit, we'll just take that as a good starting point for understanding magnitude here. All right, so at 10 degrees Fahrenheit, based on prior literature, we might see 10 to 20% increases in demand, 5% reductions in thermal capacity, 3% increases in heat losses, and then lifetime will respond exponentially to these factors. So these numbers maybe don't jump out at you as crazy, but there's something to consider, especially say a 20% increase in electricity demand. So we want to understand how all these factors are going to interact and think about their combined effect on distribution reliability and costs. But when we look again for studies that have examined these questions, what we find are very few studies on distribution, and all the studies that exist in this area are about individual parts of the distribution system. So let's look at this transformer or this distribution line or all the distribution lines or all the transformers. They have not looked at a distribution system operating as a network where you have demand aggregating from households into low voltage, into medium voltage, into high voltage. So those network models are going to really tell us how the network is being affected. So here's an example. The left-hand schematic here is a very simplified version of a distribution network. You have high voltage distribution lines. Above them are transmission lines coming in. They come into a substation. They step down to medium and low voltage. And then you have a bunch of households on feeder lines. And most of our distribution networks are radial, which means power flows through one or two avenues to your household. It's not like it's got 1,000 different routes it can go to your household. All right, so some of the papers in this area, for instance, this Bartos and Chester paper, it's just looking at transmission line capacities. They see reductions of 2 to 6% due to climate change. And then this other paper is about distribution line capacity reductions. So just the line capacities, not thinking about demand increases, interacting with transformers, interacting with line ratings. All right, and why this network model really matters is we can take these numbers on the left-hand side here. Let's say we have an overall expectation of a 10% increase in how much power is flowing through our transformers or through our power lines. 10% might not be bad, but 10% could really mean In some places, it's a 2% increase, and in some places, it's a 30% increase. And the aspect of the distribution network that's very important is because of its radial manner, this stuff does not get smoothed out across space. You're going to have large variation within your distribution system in terms of flows and the potential impacts. And so with a network model, we can get at, is it 30% in some places or is it 10% everywhere, which seems more manageable? All right, so we want to do this network analysis of climate-driven impacts. Studies haven't done this before. We want to answer 3 questions with our network analysis. We want to first understand the impacts on distribution network performance from climate change. We then want to ask, what does that mean for grid reinforcements? Are you overloading a lot of your assets, transformers, and lines, so you have to replace them? And if you have to replace them, that means somebody's paying for that. It's increasing costs. So we want to estimate how much it's going to cost to reinforce your grid to deal with climate change. So we're going to have 3 different sets of questions, one feeding into the next. All right, to answer these, ultimately what we want is on the right-hand side here. Performance, investment needs, costs. Those are the 3 quantities that we're after. We're going to build up left to right to get there. So we're going to start with our key inputs. 2 inputs that we need is climate data, future weather data, and our distribution networks. So our climate data, we're going to take from a data set called the Thermodynamic Global Warming data set. It's 4x4 kilometer hourly climate data across several RCPs for the entire country. So this TGW data set is publicly available. We didn't make it, we're just using it. Happy to refer you to it if you're interested in using it. But it's a great data set. It gives you a sense for future climate change at very high resolution. So we're going to take that and we're going to look at a moderate warming scenario. Probably what we're on course for right now, if not a bit optimistically aiming for. And then for the distribution network, we're going to use NREL's SmartDS dataset. SmartDS is great because it is synthetic and it is an at-scale realistic distribution network. There are 3 of them: San Francisco, Austin, Texas, and Greensboro, North Carolina. You can see the map here is the map of the distribution network. So there are millions of customers represented, households, lines, transformers. These are built to mimic the actual distribution networks in these locations. So they're huge, they're validated on the actual networks. They're a great resource for doing real-world informed analysis. All right, we're going to take the climate data and the distribution networks, and we're going to do 2 different analyses to them. First, we're going to model buildings, individual households, and their demand for electricity. That's going to be affected by your climate data. And the distribution network has household representations within it. So that's what we're going to use. We're going to use a neural network model to estimate building demand under future climate change. That's going to entail mostly heating and cooling. And then we're also going to affect our transformers and lines with the climate data, changing their capacity from bottom-up physics-based equations. So in general, our climate data is going to make things hotter, which means more building demand for electricity and lower capacities in your transformers and lines. We're going to feed both of these into an AC power flow model that's going to optimize flows across the network. We're going to use a weather-dependent model here, which is capturing the effects of weather on your building demand and your transformers and lines. And from that AC power flow, we get loading levels, we get voltage levels, which gives us then our performance, our investment needs, and our costs. All right, so 3 networks that we're going to look at across the United States under this moderate warming scenario. Okay, so with this framework, we've got these 3 buckets on the right-hand side that we're going to answer in turn. We're going to start with network performance, then we're going to talk about investment needs, and finally, we're going to talk about costs. So our performance, the key metric we're going to use here is loading, which tells us how much power is moving through the line as a % of its capacity. So if you're loaded at 100%, you have as much power as you really want moving through that line. You don't want to go above that value. And so the more you load up an asset, the faster it's going to degrade, but also you're just approaching safety limits. So we're going to look at loading first. We've got our 3 cities in each of these groups of ridge plots. And then the top are our distribution lines. The bottom is our transformers in each of these locations. And this black line is the 0% here of loading difference. So this is how climate change is changing loading. We're comparing historic to future, and we can see loading is increasing by about 2 to 5% at the median of these distributions. Some places like Austin are at the higher end, some places, San Francisco, at the lower end. And while that median is only 2 to 5%, you get quite long tails, especially down here in the transformers. Your transformers, your 95th percentile values are 8 to 11%. So pretty large increases in loading in your transformers at least, but also in some of your lines. All right, so higher temperatures, more demand, less capacity, all driving higher loading of your network. You might not care about loading though. Utilities do, but maybe we don't because it's not really accessible to us. So let's translate loading into investment or reinforcement needs. And to do that, we have to understand how utilities think about updating or upgrading their distribution networks. So we're going to think about reinforcement needs across 3 buckets. And these are based on conversations with utilities across the United States. These are going to be based on thermal loading level. We're going to look at 3 levels. If you're up to 70 or 80%, depending on whether it's a line or a transformer, you don't need to reinforce that line. You are fine. You're in a good operating regime. You're not worried about it. You're just going to sit on it. If you're above 80% loading at any given point, that's a candidate reinforcement, which means we would like to replace it. We're going to put it on our list of assets to replace and get to it when we can. Most utilities across the United States have a backlog of reinforcements that they're trying to make. So this is like, we're going to get to it when we get to it. When you get above 100%, that's when we get into the critical reinforcement bucket, and that goes to the top of the line for replacement. So that's when that is urgent to a utility to deal with. All right, so we're going to take the loading of our assets and think about, are we moving between these loading classes? So again, here we're going to just divide between transformers and lines, transformers on the left, lines on the right. And within each of these subplots, we have our 3 regions: Greensboro, Austin, San Francisco. And on the y-axis here, we've got the increase in investment needs driven by climate change. So this very first bar is for Greensboro transformers. We see about 3% increase in your critical replacement needs, and then another 5% increase in your candidate replacement needs because of climate change in your transformers. In Austin, it's a little bit less in both categories. San Francisco has a much smaller effect than Austin or Greensboro. And then your lines, these are 2 different y-axes. Your lines, you have lower percentages of each. So here we're seeing you do need to invest more. You have more reinforcement needs because of the increase in loading. Because as you load up more, you're moving assets from being safe operating regime to candidate reinforcement regime to critical reinforcement regime. And that's happening with assets that aren't dangerous as well as being upgraded from candidate to critical. Now, 9% might not seem much. Greensboro, you're going to think 9% increase in reinforcement needs. But remember, these distribution systems have thousands of transformers in them. And utilities are already dealing with a backlog of replacement needs. So 9% of thousands in a system where you're already have a backlog is a large increase that is meaningful to the utility prioritizing work and scheduling work. We can look across space because we have these actual networks that are realistic and grounded in locations. So all of these networks, the black circles are showing you where reinforcement has to be done because we've crossed a candidate or a critical threshold. And we've also here showing you low versus medium versus high voltage, which we track in our results. So most of our assets that we have to reinforce are low voltage because there's way more low voltage assets, but you get some medium and high voltage assets as well. And because those medium and high voltage assets are much larger, they account for actually a majority of your capacity investment needs because just a few medium or high voltage matter a lot in terms of overall capacity. All right, so we've got our investment needs. The final thing that we wanted to look at was costs. What is this going to cost for us to deal with? We've got 2 different ways of thinking about these costs. We can think in total numbers over the next 40 years as we deal with climate change, or we can annualize the costs per customer in each of these territories' footprints. So maybe the right-hand side is where you want to start because that's the annualized cost per customer. You maybe know how much you pay, or you can relate to paying $800 a year in your utility bill to deal with these upgrade costs. So We've got each of our cities here. Now our bar plot is split into two. We have a reactive and proactive. Reactive is a utility sitting back and not thinking about climate change, not worrying about climate change. Just saying, I'm going to replace my assets as they reach candidate or critical loading. So you might get an asset that overloads, you might go and replace it, and then 10 years later, you're replacing it again because temperatures have increased even more. Proactive is when you replace that asset, you look into the future and you proactively deal with warming coming at you. So the reason there's such a large difference here is because looking ahead is going to avoid some redundant investments and help you save in terms of overall investment costs. In Austin, for instance, you go from a cost per customer per year of about $700 down to about $250. Now, that's a huge savings. That's like a two-thirds saving. I'd still say $200 per customer per year, especially today with how costs are, is a large cost to be bearing. And this is entirely driven only by climate change. The left-hand side shows you total investment cost. That's approaching $1 billion, for instance, in Austin with the reactive framework. And Austin and Greensboro have higher costs. San Francisco has much lower costs because we saw it has lower reinforcement needs. All right. So overall, this study looking at distribution systems with climate change, you get more loading, more reinforcement needs, more costs to reinforce your network. And I told you our study would only look at climate change here. We would discuss qualitatively decarbonization after. And so I just want to briefly mention climate change is not the only stressor on our distribution networks. Probably many of you work or think about distributed energy resources, electric vehicles, and your electrification of your households. Those increasing demands driven by decarbonization are also hugely increasing loads on distribution networks. There's a study here that looks at California. It finds you need $6 to $20 billion to cover capacity upgrade costs by 2045, just for electrification. That study was not thinking about climate change at all. So what our study indicates is climate change is coming. It's already happening. It's already reducing the hosting capacity or excess capacity in your network. And it's happening just as you need more capacity in your network to deal with decarbonization. So these two things are working against one another. And so one key conclusion that we get from this is you have to think about these drivers together. If you're thinking not proactively, you're going to underestimate your investment needs, underestimate your sizing, and that could significantly increase costs for ratepayers. All right, so our second study on distribution systems finds climate change-driven loading is going to really increase your costs, especially if you're not proactively thinking about coming warming, and it could constrain your electrification. The last scale that I want to work on then is at transmission scale. We went from electric vehicles, individual technologies, up to distribution systems. Now we're going to get to transmission systems. And here we're going to, again, go back to thinking about decarbonization and climate change hand in hand. And here what we're going to work with is your climate change is going to affect your ratings of your lines. Your decarbonization could force you to change how your rating standards. And so these two things are going to interact. We want to think about these interactions in this final segment on transmission scale systems. So just to make sure we're all on the same page, transmission systems are those giant power lines that you see while you're driving along the highway. It's the highway system for electric power across the nation. All right, so the starting point for this paper is the reality that climate change will reduce our transmission line capacities. There are several papers on this. This is one example that I've pulled, a Bartos paper from 2016. This percentage is showing you the decrease in transmission capacity across the United States for some warming level. It's a moderate warming level. So you can see those decreases are somewhere between 2 and 8% of your transmission line capacity. This is happening because transmission line capacities, or how much power can move through them, is a function of several weather variables: temperature, solar radiation, and wind speed. Basically, this is a heat balance that's happening in your conductors. You want to balance your heat that's accumulating in your conductor. Higher temperatures, more solar radiation heats up your line just as it does you. Wind will cool off the line. And so higher temperatures, more solar radiation, more heat in your conductor, less capacity. more wind coming through, more capacity. When we think about ratings in current power systems, we typically use static ratings. And a rating is what the system operator is trying to keep power flows to. So the capacity is how much could possibly move through it. The rating is what we want to keep flows below. And typically what we use in current systems are called static ratings. It is a constant capacity that is calculated using conservative assumptions. So this right-hand side here shows you what a static line rating looks like. The level of 1 is just set to the static rating. It is their hours of the year on the x-axis. The line isn't changing because the static rating is static. It doesn't matter whether it's hot or cold or windy or sunny or whatever is happening outside. The rating of the line does not change. It's a static rating. But our ratings, we can also vary with weather depending on the rating standard that you use. And so these are typically called dynamic ratings. There are several different types of dynamic ratings. But in general, they're going to vary the rating of your line to account for the fact that when it's cool outside, your line capacity is higher. And when it's hot outside, your line capacity is lower. When it's really windy, you can move more power through your lines. When it's not windy, you can move less power through your lines. So rather than have a static rating that is totally flat through the year, your dynamic ratings will vary hour to hour or day to day or week to week or month to month, whatever time scale the utility chooses to use for their dynamic ratings. And while we're going to use hour to hour throughout our analysis, utilities often use daily or weekly or monthly timescales. And these dynamic ratings are not just some hypothetical thing in the future. They're being used across the country. Ambient air ratings, a type of dynamic rating, are actually used in Texas already today by ERCOT. And there's a FERC order that said all markets must support dynamic line ratings. So there is movement towards using more and more of these dynamic ratings. So it's happening. What we want to understand here is the interaction that we're going to get between climate change affecting your capacities and transmission rating systems evolving over time as our technology enables new rating systems like dynamic ratings and as decarbonization drives interest in dynamic ratings. So our research question here is, can dynamic transmission rating schemes mitigate your transmission investment needs driven by climate change? Climate change is reducing your capacity, which is probably going to increase your investment needs. Can I reduce those investment needs through these new rating schemes, through these dynamic rating schemes? All right. So again, a very simple methods framework for the study. We're going to start with climate data. This is going to be, again, high resolution. It's called dynamically downscaled weather data. It's 4x4 kilometer hourly data, really good, produced by climate scientists. We did not make it. Again, it's free to the public. We're going to take that weather data and we're going to rate transmission lines with different approaches. We're going to look at transmission line ratings with static ratings and with different types of dynamic ratings. We're also going to use the weather data to create wind generation profiles, solar generation profiles, demand profiles, hydropower generation profiles. So everything is consistent in our model. One set of weather is driving all of the factors in our modeling framework. And that modeling framework is going to be Pipes of USA, which is a large-scale system model. It's like a capacity expansion model. It's going to look, in the long run, optimize investments and operations. And so what we're going to get out of all this, the key things that we're going to care about is transmission and generation investments. How much do you have to invest between now and 2050? So a little more detail on each of these parts. We're going to pull weather data from several different types of climate models to capture uncertainty in those models. We're only going to apply dynamic ratings to lines below 100 kilometer, according to industry practice. And then in our Pipes of USA model, this is just a little bit of the math formulation. The most important part here is we're going to run this with a set of DC OPF constraints. So we're capturing to some extent power flows across the transmission network. And we're going to run our analysis on the Western United States. That's the map here in the bottom right. We've got about 800 lines and 350 buses in this system. So pretty good resolution. We're still simplifying the system, but for the size of our network, it is tractable. All right, so first let's look at the ratings that we're going to analyze. Then we'll look at the investments that we get out. So we're going to compare 4 different types of ratings. We're going to compare two static line ratings. Static ratings do not vary across the year. We're going to start with a static line rating that ignores climate change, and then a discounted static line rating that is looking ahead at increasing temperatures and is basically a little less than our static line rating. So the discounted static rating is what if utilities didn't change their rating practices and instead just thought about it getting hotter? That's our discounted static rating. And then we're going to look at two dynamic ratings, ambient air ratings or ambient adjusted ratings, sorry. This is what's used in Texas and in other parts of the country. What these do is actually give you more rating, reflecting that there's more capacity on the line, because most of the time it's cooler than your assumption for the static rating. So the blue dots here are your hourly ratings. You see those blue dots above these solid lines. That is because, again, you have more capacity than you think with the static rating, so your rating is higher to reflect that. There are some periods, though, where you have less, and those are during extreme heat events. For instance, the second dynamic rating that we're going to look at is dynamic line ratings. These are sometimes called real-time capacity. They're similar to ambient adjusted ratings. They just lean a little bit heavier on the weather data that you're using. And so you can see the blue and the green, they have a similar shape. They're going up at similar times. They're coming down at similar times. And again, both of these have less ratings during really extreme heat events, but generally higher ratings available to you. All right, so we're going to compare these four ratings and their effect on transmission needs. And the transmission needs are going to come out of our pipes of framework. So let's look at our investment needs across these modeling frameworks. All right, first we'll look at generation just to ground us in what we're actually building in these systems. We're looking out to mid-century, so around 2040, and what we get is a lot of investment in wind and solar. This is kind of like a validation. It's good that our model says we're building wind and solar because that's generally what most people expect to be built in the long run, notwithstanding what might be happening at the current point in time. The left-hand figure is where we start, so this is our base system for WEC. And then the right hand are the different investments. We've got 5 different climate models, which means 5 different sets of weather data, which means 5 different sets of investment needs. And so we're going to look at consistency across these climate models. Basically, they're all building roughly the same thing. A lot more wind and solar, retiring coal, gas, some nuclear, some combined cycle as well. All right, so we're getting this shift in our generation portfolio, indicating, all right, this model is operating roughly like I'd expect it to. What we really care about are our transmission needs. So let's look at what's happening with our transmission investments. We're going to start with our static line ratings. The top right here is reminding you what that static line rating looks like, a flat line across the year, and we're going to drop that static line rating a little bit to reflect rising temperatures. So what we get first is an increase in our transmission investment needs. This is saying climate change is increasing temperatures. Your static line ratings must decline in response, so you need to build more transmission capacity. And this is about a 5% increase in capacity needs. Different models at different amounts, but about 5%. Now, 5% might not seem like a lot, but in general, we're building a lot of transmission investment moving forward in this model to better integrate renewables, to reduce our system costs. And so the delta between what climate change is doing to increase our investment needs is basically how much we will need to build at the current US build-out pace over the next 25 years. So it's a 5% savings, which seems like not a lot, but since it's so hard to build transmission capacity in the United States, that actually makes this problem quite a bit easier by avoiding the current US build-out pace over a 25-year period. But we don't really care about just the static line ratings. We're interested in the dynamic ratings and how it can change your investment needs. And so we want to now look at dynamic ratings. We have those 2 different types, ambient adjusted and dynamic line ratings. They're quite similar, so we can just think of them collectively as dynamic ratings, changes in time with your ratings. And so here, instead of seeing an increase in transmission capacity, what we get is a decrease, which means even though climate change is happening, when we add on these dynamic ratings, we have to build less overall. So it is saving us in our transmission investment needs. Ambient adjusted ratings do it a little bit better because we're avoiding more reliability upgrades. And we can look not in terms of percent, but in terms of overall terawatt or total capacity of an investment. And we're adding these AAR and DLR, the ambient adjusted ratings and the dynamic line ratings, onto what we understood before with our static line ratings. So again, we see this big drop in how much we need to invest. And I just want to emphasize, 10% might not seem like a lot, but because it is so hard to build transmission capacity, that is really meaningful savings, especially compared to the current US build-out rate. So overall from this study, what we're seeing, climate change will increase your investment needs if you do not change your rating scheme, but a lot of systems are changing their rating schemes for non-climate change reasons. And when we account for that, in addition to climate change, we really reel back how much we need to invest in response to climate change. Okay, so our takeaways here are at the bottom. We get increase in transmission investment needs because of climate change, but when we account for dynamic line ratings, we're neutralizing those investment needs. So the bottom line here is, if you think about decarbonization and climate change happening at the same time, that joint perspective really radically changes your understanding of your investment needs, because the decarbonization investments are acting double as your adaptation investments as well. And so you're not seeing a large increase in investment for climate change. You already got that through your dynamic line ratings for decarbonization. All right, I told you my mission today would be to convince you that we have to plan for decarbonization and climate change. We went through 3 different scales: electric vehicles, distribution systems, transmission systems. We saw in each of these situations, there's strong interactions between decarbonization and climate adaptation, whether it's decarbonization providing co-benefits for adaptation, or whether it's additional conflicts between the two that requires a lot of careful thought moving forward. So hopefully you are convinced accounting for both of them is important. I really appreciate everybody's attention, and I'd love to answer any questions that you all might have.
There we go. Missing my button to come back in. All right. Thank you very much, Michael. We do have a few questions here. Keep your slides up. There's at least one question for one comment there to show the variables that affect transmission line capacity. I think maybe the heat balance slide, just for the person asking here. And I think you answered the question. Of course, you were maybe thinking about answering it, which was, do we need more transmission lines or different types of transmission lines? And there's even a question about more dense housing. So I'll add on to that. You kind of ended with, looks like, maybe we can handle even less, or the existing amount of transmission line. I guess some of it might have to be replaced. Of course, we have the perhaps ever present question of data centers and artificial intelligence. So you want to just say what you've thought about that. You've thought about different future scenarios, of course, here, and electrification and climate, and of course AI is there for the electric demand. So yeah, how do you think about the results you've shown in light of just what we know now, maybe within the last year or two?
Sure. So I get like I categorize those as quite different factors. The electrification feels it is very uncertain how much demand growth we're going to get from it, but it's such a distributed set of investment decisions that you have some certainty about what that's going to look like in the future. In fact, in the household work that I was going to present but didn't, we look at how much that uncertainty in electrification is relative to climate-related uncertainty. And actually, over the next 20 years, it's really climate-related uncertainty that dominates overall demand uncertainty. It matters a lot more than your uncertainty when it comes to electrification and driving peak demand. The data centers, none of this work touches on it. It was all done before or in the midst of all this, when there's so much uncertainty about how much is going to be built. It seems like the more data centers that you get, the greater needs in transmission investment you're going to have, most likely, unless there's all this bring your own generation that the data centers do. And I guess to me, I'd be very interested in understanding where those transmission investments are going to occur, because what we don't want to do is build a bunch of transmission, just for data centers and have it not provide much value to the rest of the system, or from my perspective, also to provide double value in terms of climate adaptation. And so I think that would be really interesting to look at where data centers are being sited and what your options for distribution or transmission network upgrades is, so that you can make those upgrades while thinking about what you're going to need to upgrade anyways down the line to deal with climate change. And I don't really have intuition for that because, I read data center reports now and then, but it changes so quickly that it's hard to keep track of where things are in that space.
Right, no problem. Uh, Here's a question on maybe seeing if you can play out an example of the sort of proactive distribution level investments to deal with climate change. So, do you have an example that helps make it more real for someone, what it would mean for a utility to make a different type of proactive investment?
Yeah, so there's lots of distribution utilities. I shouldn't say, yeah, lots that are already doing this, that are thinking proactively about climate change. Two that come to mind, Con Ed in New York and SoCal Edison in California. They both have climate adaptation plans. Cava is one of them. I don't remember the other one, where they have looked at each of their assets on the distribution networks, looked at their exposure to increasing extremes under climate change, and done, an asset by asset accounting of their risks to climate change. So that's great. And so they worked with climate scientists, they brought in climate data, they did that, and they can categorize, oh, these transformers in these region are vulnerable to heat, or we've got some substations along the river here. We're worried about sea level rise and storms, so those are vulnerable to sea level rise. So that asset by asset accounting, I'd say, is um, a good practice and is what some utilities are starting to do. Our analysis, though,
But
is trying to go past that one step, which is just to run a network analysis so you can understand not just asset by asset, but how flows are accumulating through the network, how demand is interacting with your asset impacts. And that right now, we don't really see happening. That could be for a variety of reasons. One is it's just very hard to get climate data that you'd want. And there's some other changes in planning practices, like using time series and power flows for your planning decisions, rather than selecting time periods or critical periods and using those for point estimates in terms of loading. And so our paper goes into like different practices that utilities use that I'd be happy to share, and how our strategy can kind of integrate into existing practices to provide a better way forward in terms of being proactive.
in terms of, you showed one example is the mapping out, I guess, vulnerable transformers on this synthetic grid. Does it mean they invest in a different type of transformer, a higher power rating transformer or something? Or what does,
Oh, I see. Sorry.
proactive mean? Yeah.
I think most of these are, it's not a different type of transformer. It would just be upgrading the capacity of the transformers. And for your medium and high voltage, that means you can expand what's already there because they're modular in that way. For your low voltage, like your pole mounted transformers, that means you're replacing it for a similar type, just with a higher capacity. And your lines, you have a few different options with as well. But a lot of it is probably going to be reconductoring for your lines.
Right. Okay. Good. I mean, this map here, I don't know if you have a feel for this of, how many transformers are there? And I don't know if these dots are, I can't recall, these are transformers or just lines or some combination of factors, but
Oh yeah. We- I mean, even the whole regions, like Smart DS is so great that, like San Francisco here, there are 3 or 6 different regions within the Smart DS data set for San Francisco, because this, is a very small part of this full Bay Area. So we're doing all these subregions within each of these distribution networks. They have tens of thousands of transformers, if not hundreds of thousands. I don't remember the full sample size, but there are a lot.
okay. Didn't know if you just had a feel for that. So a question on sort of the EV batteries and lifetimes or degradation. Do you understand if there's an effect from humidity? That person was commenting that maybe, India looked like it was more impacted or not. And go ahead.
Yeah. Oh, I'm sure. we dealt with that because the weather data set that we use, we're pulling, we're dealing with temperature. We've got solar radiation, which increases temperatures in the cabin. We've got humidity in there. We've got a battery thermal management system that we're simulating as well to try to be as accurate as possible in terms of how these vehicles actually operate. Um, I don't remember how strong the effect of humidity is, but I do not think it was strong. If you want to email me, I'd be happy to send you the paper. It will be out in a couple weeks, and I'm sure we have that in the essay somewhere to what extent humidity matters.
Right. And on the, I think a few slides later than what you're showing there, for the new batteries, you have, at least within the uncertainty or the variation, there's some increases in battery capability, seemingly as a function of temperature. But then that, I think your graph indicates that's because of the loading or the charging method. Do you have an understanding for, I guess, why you can get an increase with temperature based upon how you charge, or am I
Yeah,
interpreting that wrong?
it's a matter of, since we use a full time series of climate data, we oh, there's more extreme heat, but there's also less extreme cold happening in the future. And so your old batteries are so vulnerable to the extreme heat that increasing extreme heat washes out any benefits you get from less extreme cold and reduces the lifetime basically universally. But your new batteries are durable, they're more resistant against extreme heat. And so as climate change is eliminating your lower tail, eliminating the extreme cold, you get more lifetime benefits from less extreme cold than you get lifetime reductions from more extreme heat. So that balance actually changes with the new batteries so that you get lifetime increases because of less extreme cold. Like between these two scenarios, charging is not changing, driving patterns are not changing. The only thing that's changing is the batteries and then the effect of climate change. And so it really is just less extreme cold has a really good benefit for lifetimes for new batteries.
Right. Okay. So I think you're saying that batteries have, in some sense, are designed for a sweet spot of temperatures, and too hot and too cold is bad, and we're just shifting to where the battery is between the too hot and too cold. Okay. Here's one maybe somewhat related to the work you didn't talk about in heat pumps, but this one's just kind of about heat, I guess, heat or cooling loading on homes, and green roofs, painting houses, things that can be done to reduce the load in homes. And I guess you've thought about heat pumps. So is there anything you want to just maybe try to summarize from that type of work about household heating and cooling that's important here?
Yeah, why don't I just go down to one of those slides? So I heard green roofs, white roofs. Unfortunately, we don't look at anything like that. So I don't have any direct insights on that. Those types of mitigation strategies are going to compete with your rooftop solar and other things that you might put on your roof. And so there's that competition for rooftop area that might make those mitigation strategies less appealing. Our study on heat pump looked at heat pump and envelope upgrades, so like more insulation, better windows, so increasing the overall efficiency of the household. And the key message here was we wanted to understand the effect of just heat pumps and household insulation, just climate change, and then the combination of the two. And these figures are showing you peak demand over time for different ISOs or RTOs or regions in the United States. And so you can see like in these cold regions in the top there, the main finding from this work is there's a strong moderation between these two forces of climate change and technology diffusion. You think demand might skyrocket with more heat pumps and more insulation, but because climate change is changing your temperatures, it really reels in that demand increase in many regions. And you can look at Texas, for instance, is in the very bottom right here. Again, you get less demand with technology diffusion because of more efficient heat pumps. That is mitigated by warmer temperatures driving overall cooling demand increase. So the overall purpose of our heat pump paper or finding is there's a strong moderation over time between these two factors of technology change and climate change.
Yeah, well, I guess we sort of chatted on this before we started here. And of course, in Texas, we're perhaps a lot of the country still thinking about Winter Storm Uri 2021, which is, I don't know, a polar vortex. So I don't know how much these things are considered in these climate scenarios or not. And it's not an every year phenomenon, or at least we don't. I'm not a meteorologist, but I guess don't expect it to be every year. So I don't know if you have any insights on what's you not being a climatologist either in terms of these scenarios and the extremes that are within them.
Yeah, so different types of climate data sets capture the extremes better or worse. Actually, in this paper, we're using what's called a SMILE. It's a single model initial condition large ensemble, which just means it's got a lot of climate realizations in it. So this particular paper, in every year, like 2030, we have 40 different realizations of weather in that year. And then the next year, 40, and the next year, 40, and the next year, 40. So we get a very large sample of extremes in that climate data. So we've not looked through it for Winter Storm Uri in Texas, but this is the type of climate data set you would use to capture extreme cold events moving forward. So I feel confident that our results are implicitly capturing that. This figure that I'm showing you here, we looked at the timing of peak demand, again, under just climate change, just technology change, and then their combination. The key takeaway is you get lots of red at the top, everything's summer peaking. With technology change, you think, oh, places are going to become winter peaking. But the combined effects is a lot of places that were going to winter peak are not anymore because it's getting warmer. There's less extreme cold events. You can see Texas second to the bottom there. It's solidly red. So, only summer peaking basically for Texas moving forward under any one of these factors, but especially with climate change is what this paper finds.
All right, we'll just make a joke that the red and blue here are about temperature. Okay. We'll end on perhaps this one, which is not that you're here to give investment advice, but you might suggest it. So looking at, you talked about the EV battery degradation. This person's asking, well, it sounds like it's best to buy a used EV after 2019. They have better batteries or something.
Yeah, Volt, that's for sure. Yeah, I think that is right. And like the durability is really important for the resale market. It's not an area that I work, but my colleague Parth Vaishnav here works a lot on it. And yes, if you're gonna buy a used EV, I would definitely buy the most recent vintage that you can find because the durability is going to be better and the battery health when you get it is going to be better. Yeah, and like we're not the ones who came up with this figure that shows the immense increase in lifetime coefficient. Like this is well established from other work. So yes, recent EVs used, I think, are premium assets. And this is again there's like lots of interesting empirical work because there's large EV vehicle fleets. There's companies that provide data for resale and for resale for buying used EVs. And so you can also see that just in the empirical data.
Right. Well, I was gonna, it sparked my curiosity on this one, and this is as you say, somewhat an older paper in the EV battery space, roughly 10 years at 60 degrees centigrade. Is that a sort of the temperature within the cell? I mean, within the battery pack itself that's expected, and how much of this perhaps better battery performance is battery management versus chemistry, or do you have any idea there?
I think it is a combination of the factors. I think this 60 degrees Celsius is probably temperature in the cell pack, yes. How Chu, if he was giving the presentation, the first author here could talk to you for 20 hours about all the different factors here, but it's a combination of them all. Better BTMS systems, better chemistry, better packing methods, and lots of other advances that overall improve durability.
Right. Okay, thank you very much. So we'll end it right there. So again, thank you, Michael Craig, assistant professor at University of Michigan. Thanks for joining us here on the UT Energy Symposium and helping us understand the impacts of temperature on energy infrastructure. Thank you very much.